Okay, everyone. Now let's talk about the definition of stiffness matrix by using the OneNote of Microsoft over here. So to simulate the environment of a in-person teaching over here. So firstly, as we have already shown in the module one, typically when we do finding the element method to solve the physical or engineering problems, the first step is to formulate the stiffness matrix for a element, which can be seen as a smaller part of the system that uh, we are investigating. So typically for an element, so the stiffness matrix describes the relationship between the displacement and the forces acting on the element. Right? So we have a stiffness matrix, the K, where we use a lowercase k here, and is a matrix uh, such that we have the relationship between the elemental forces. We use the lowercase f to represent the elemental forces equal to the stiffness matrix times the elemental displacements. So we can have the K relates nodal displacements, nodal forces F of a single element here. So typically for a element, there will be multiple displacements because in order to um, describe the geometry of a system, you need at least 2 points in the space, right? So that means 2 points, you may all have multiple displacements in different directions. Similarly, for the forces, so we use a stiffness matrix to describe the relations between displacement forces. So we start from the easy simple easy example, right? Such as a spring element, right? So for a spring element, we will have so for example, we use two loads. We have the node one and the node two here to describe a spring. So between the two nodes, we have the spring here, spring here. So we can also define a coordinate system here. We have oops, the x direction. That is a line of the element. So the x is called the nodal coordinate system. Nodal coordinate system in here. So with this information here, we should be able to start the derivation of uh, uh, the stiffness matrix here. So for example here, we consider the displacements. So for node 1, and we have the displacement in the x direction, because the spring can um, extend or shrink over here. So we have the u1. So u stands for the displacement in the x direction. Similarly, and we have the displacement 2. So that's the displacement of node 2 in the x direction. So we use u2. How about the direction perpendicular to the axis? Yeah, because this is a spring element, and for spring we don't consider the moments perpendicular to the spring. So here, when one axis or one direction, for the displacements will be adequate in this case. That's all. That's all we have for a spring element. Regarding the displacement, and regarding the displacement. So similarly, we consider the forces. We consider the forces, and I'm going to use a different color. So we have the force applied to node 1. That's called F1. Force applied to node 2. That's F2. F2. So we have all the forces and all the displacements here. So here we can write down the force this matrix should be equal to F1 x. We just use 1x, F 2x. Yeah, because we would like to know where the where the forces are applied on, and which directions are these forces. So we need two subscripts here for each force here. So similarly, for the displacement, we have the u1 and the u2. Here we do not need the x because u stands for the displacement in the x direction. This is for a spring element. So how about k? K here that remains here is unknown for us to determine. So after this, we will in the same module we will discuss the theory or the theoretic procedure to figure out what would the elemental stiffness matrix look like for the spring element here. Okay, so this is a spring element. So if we have a structure, for example, if we have in most physical or engineering problems, we deal with a structure. So we have a structure composing of a series of elements, such as if we have a structure system composed of three springs here. Yeah, if we consider a three springs forming a triangle over here. So in this case, we will have 1, 2, 3. And we will have 3 nodes here, so we have 3 elements. So in this case, because of the geometry, we need the x and the y. Need the x direction and the y direction. So this is a global coordinates. So here we will have the forces. We have all the forces in. So firstly, let's consider the displacement. Because of the geometry, we need to consider both the movements in the x and the y direction. For example, for node 1, we will have the u1 and the v1. And for u2, for node 2, we will have the u2 and the v2. Node 3, v3. Sorry. Similarly, we need to consider the forces. Forces, we have the F1x, F1y. Now, since that's global, so we use uppercase. We use uppercase. F2y, 2x. We have F3x, F3y, F3y. So those are the displacement forces we need to consider for a two-dimensional geometry. So for one-dimensional geometry, typically we need to consider fewer forces and displacement. So here we can write down the force matrices in the global coordinates. So we have the 1x, 1y, 2x, 2y, 3x, 3y. We have the d, so that's equal to u1, v1, u2, v2, u3, v3, v3 in this case. So here we can also define the global stiffness matrix. We have the global stiffness matrix. Here we use the uppercase key. It relates the global coordinate the nodal displacements to nodal forces. This is we have the F. Using the D here. So such as we have the F equal to K times D, where we need to figure out, like anytime when we start the finite element analysis, we need to figure out what would be the global stiffness matrix here. Yeah, so that's a definition of the stiffness matrix. Basically, for any problem, um, given the geometry, we should be able to figure out after we select the type of element, we should be able to uh, define uh, the force and the displacement matrices there. So the next step is to figure out the relations between the forces and the displacements. Typically, we start from the element level, and based on the element level, we should be able to use a very straightforward process to find the global um, relations here. So that's a definition of stiffness matrix. And that's all for this topic. After you do some um, exercise on there is a topic we will talk about the derivation of the stiffness matrix for a spring element. So how would the elemental stiffness matrix look like for a spring element? Thank you.